In 1814, Pierre-Simon Laplace imagined an intelligence that knew the position and momentum of every particle and understood every force. Such a mind, he argued, could compute the entire future of the universe and reconstruct its entire past. He called it a demon. Not a malevolent spirit, but a calculating engine of perfect knowledge. If the universe runs on deterministic laws, then prediction is merely a problem of accounting. The demon knows what you will do tomorrow because the particles that compose you already move in a pattern that permits one outcome. For a century, physics seemed to deliver on that promise. Newton's laws predicted planetary orbits. Halley's comet returned on schedule. The tides obeyed equations. But the demon is dead, killed by three discoveries: chaos theory, quantum mechanics, and the physical limits of computation. Beneath those three deaths lies a question that refuses to die. If the block universe is real, if past, present and future all exist together in a fixed four-dimensional structure, then what do we mean when we call an outcome random? Stay with me and you will understand why Laplace's demon was not simply wrong, it was asking the wrong question. You will see how determinism and unpredictability coexist, how randomness might describe compression rather than reality, and how a fully determined cosmos could still slip through a narrow door. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. So, this is where it begins. Laplace wrote his demon into existence in 1814, in a philosophical essay on probabilities. A mathematician and astronomer who had spent decades refining celestial mechanics, Laplace believed that any reliance on probability stemmed not from the world, but from ignorance. Know enough, and probability vanishes. His demon made this explicit. An intellect vast enough to hold the position and velocity of every particle, and sharp enough to apply Newton's laws, would render the future as certain as the past. Nothing would remain uncertain to it. The whole sweep of history, from the first instant to the last, would lie before its gaze as a single, legible pattern. For a time, the demon seemed nearly within reach. Astronomers predicted eclipses centuries in advance. Engineers built machines whose gears turned with metronomic regularity. The success of Newtonian mechanics suggested that the universe was, at its foundation, a vast and intricate clock, wound once and ticking forward according to immutable rules. The only barrier to perfect prediction seemed practical. We could not measure finely enough or calculate quickly enough. Those looked like technical problems, not problems of principle. The first crack in that edifice appeared not in physics, but in meteorology. In 1961, Edward Lorenz, a mathematician and meteorologist at MIT, was running a computer simulation of atmospheric convection. He wanted to rerun part of a calculation, so he typed in the numbers from a printout as his starting point. The printout showed values to 3 decimal places, 0.506 for example, while the computer's internal memory stored them to 6, 0.5061 0.27. Lorenz assumed the difference was trivial. He restarted the simulation and went for coffee. When he returned, the new run had diverged wildly from the original. By the time the simulation reached the equivalent of a few weeks of weather, the two forecasts bore no resemblance to each other. The system Lorenz was studying is now known as the Lorenz system, a set of three coupled differential equations describing convection rolls in the atmosphere. Those equations are entirely deterministic. No randomness is written into them. Given the same starting point, they produce the same trajectory every time. But Lorenz had discovered that the trajectory is exquisitely sensitive to the starting point. A difference of 1 part in a million grows exponentially. The rate of that growth is quantified by the Lyapunov exponent, denoted lambda. For the Lorenz system, the maximum Lyapunov exponent is approximately 0.906, positive, meaning nearby trajectories diverge rather than converge. A 2025 analysis refined that number to 0.90642, with a 95% confidence interval spanning only 0.90628 to 0.90655. This is not an approximation error. It is the signature of chaos. What does it mean that lambda equals 0.906? It means that if you start two simulations with initial conditions that differ by a factor of 10 to the 15th, a rounding error smaller than the width of a proton compared to the size of a room, those two simulations will, after about 15 time steps, differ by a factor of 1. They will disagree about whether a storm forms or dissipates, whether a front moves north or south. The system is deterministic, but prediction becomes meaningless because no measurement is perfect. You cannot measure the atmosphere to 15 decimal places, let alone 50. The precision required to forecast the weather a month from now is finer than the uncertainty principle permits, finer than the granularity of matter itself. This is the butterfly effect, though the phrase is often misunderstood. The claim is not that a butterfly in Brazil causes a tornado in Texas. The claim is that the atmosphere is a system in which microscopic perturbations grow exponentially, so that any attempt to predict its state far into the future demands impossible precision in the present. A butterfly's wings do not inject energy into a storm. They shift the initial condition by an amount that after enough time renders the forecast useless. Think about this. Two surveyors hired to measure the same river, one starting from the source and one from the mouth. If, after both recheck 3 times, they disagree by 9%, you stop questioning the instruments. You start wondering whether you are measuring the same river. Chaos does something similar to time. It severs the link between determinism, where every event follows lawfully from the one before, and predictability, where knowing the present allows you to compute the future. The demon needs both. Determinism gives it the rules. Predictability gives it the answer. Chaos preserves the first and destroys the second. Lorenz published his findings in 1963 in the Journal of the Atmospheric Sciences. The paper was titled Deterministic Non-Periodic Flow, and it included a now iconic diagram, the Lorenz attractor, a double-lobed structure resembling the wings of a butterfly. Trajectories in this space never repeat, never settle, and never escape. They spiral endlessly around two unstable fixed points, switching between the lobes in a pattern that is deterministic but aperiodic, structured yet unpredictable. The Lorenz attractor is not a picture of the weather. It is a picture of the space of all possible weathers that the Lorenz equations allow. Every point on the attractor is a valid state. The system cannot leave the attractor, but it also cannot settle into a loop. This is strange. Most dynamical systems either reach an equilibrium, as a pendulum comes to rest, or enter a periodic cycle, as a clock ticks. The Lorenz system does neither. It explores the attractor in a way that looks random but is not. Run the simulation twice from the same starting point, and it traces the same path. Start one atom's width away, and after a few cycles, the two paths have nothing in common. This discovery carried a profound implication for Laplace's demon. Even in a universe that is strictly deterministic, perfect prediction requires perfect knowledge of the initial state. But perfect knowledge is impossible. Every measurement has finite precision. In a chaotic system, finite precision is not good enough. The demon would need to know not just the position of every particle to within the Planck length, but to infinite precision, because any error, no matter how small, eventually dominates the forecast. Laplace imagined a demon that could, in principle, exist. Lorenz showed that such a demon would be, in practice, useless. It could run the equations, but it could not measure the world finely enough to start them. The universe might be deterministic and still not be knowable. Chaos is not limited to weather. It surfaces in planetary orbits. Over millions of years, the inner solar system is chaotic, meaning we cannot predict where Earth will be 10 million years from now. It surfaces in population dynamics, in fluid turbulence, in the motion of charged particles in magnetic fields. Any system with nonlinear feedback, where a small change can amplify itself, is a candidate for chaos. And nonlinearity is everywhere. The equations that govern the real world are, almost without exception, nonlinear. The Lyapunov exponent is the mathematical measure of chaos. If lambda is positive, the system is chaotic. If lambda is 0, small errors neither grow nor shrink, and trajectories stay parallel. If lambda is negative, errors decay, and the system is stable. For the Earth's orbit around the Sun, if you isolate the two-body problem, lambda is 0, and the system is regular. Add in Jupiter, Saturn, and the perturbations from the other planets, and the system turns chaotic. The timescale over which we lose predictability depends on the size of lambda and the size of the initial error. For the solar system, that timescale is a few million years. For the weather, it is a few weeks. For a double pendulum released from rest, it is seconds. This is not a failure of physics. The equations are correct, the laws are obeyed. But the laws do not grant us omniscience. They grant us local, temporary knowledge. We can predict tomorrow because the Lyapunov time for weather, the time it takes for an error to double, is measured in days. We cannot predict next year because the errors compound beyond recovery. The demon dies not because the laws fail, but because it cannot hold the initial conditions to the precision the laws demand. One way physicists quantify randomness is through algorithmic complexity, a concept developed in the 1960s by Andrei Kolmogorov, Gregory Chaitin, and others. The Kolmogorov complexity of a sequence is the length of the shortest computer program that can produce that sequence. A string of 1,000,000 ones compresses into a simple instruction: print 1 1,000,000 times. Its complexity is low. A string of 1,000,000 digits drawn from the decimal expansion of pi looks random, but is also compressible because the program that computes pi is short. But a truly random sequence, say the result of 1,000,000 quantum coin flips, has complexity equal to its length. No program shorter than the sequence itself can reproduce it. This is one rigorous definition of randomness: incompressibility. Now connect this to chaos. The Lorenz attractor is deterministic, yet its trajectory, sampled at fixed intervals, looks random. If you did not know the equations, you might assume you were observing noise. In a practical sense, you are. Even though the system is deterministic, the information needed to predict its future trajectory grows exponentially. After a certain point, the most efficient way to store the trajectory is simply to run the system. The future is not compressible into a simpler rule. It is algorithmically complex, even though it is deterministic. This suggests that randomness, at least in some contexts, is a statement about compression. A sequence is random if no finite computer can compress it. But whether a sequence can be compressed depends on the resources, the time, memory, and computational power available to the compressor. A sequence that looks random to a human might be compressible to a more powerful machine. A deterministic system, conversely, might produce output that is incompressible in practice and therefore operationally indistinguishable from randomness. This distinction between ontological randomness, randomness in the thing itself, and epistemic randomness, randomness in our description of the thing, will return later. For now, note that chaos demonstrates how determinism and apparent randomness can coexist. The system is ruled by strict laws. Its future is fixed by its present. But to an observer with finite precision, finite time, and finite computational power, the future might as well be random. The demon requires infinite resources. Chaos shows that anything less than infinite is not enough. The demon dies a second way, through thermodynamics. This death is quieter but more absolute. Rolf Landauer, working at IBM in 1961, proved that erasing information, resetting a bit from 1 to 0, or discarding a measurement, carries a minimum thermodynamic cost. That cost is kT times the natural logarithm of 2, where k is Boltzmann's constant and T is the temperature. At room temperature, roughly 300 Kelvin, this is about 2.85 times 10 to the minus 21 joules per bit. Landauer's principle ties information to physics. A bit is not an abstraction. It is a physical degree of freedom, and changing it requires energy. Erasing a memory dissipates heat. Consider why this kills the daemon. To compute the future, the daemon must store the present. It must hold in some physical substrate the position and velocity of every particle in the universe. Each particle requires at least one bit of information, probably far more, since position and momentum are continuous variables. Be generous and assume 1 bit per particle. The observable universe contains roughly 10 to the 80 particles, so the daemon's memory, at minimum, stores 10 to the 80 bits. To update that memory, to run the calculation forward one time step, the daemon must perform operations, and those operations generate heat. Even at the Landauer limit, operating with maximal efficiency, it dissipates energy. Now trace where that energy comes from and where it goes. If the daemon is part of the universe, it must obey the second law of thermodynamics. It cannot run forever without a source of free energy, and it cannot dissipate heat without increasing the entropy of its surroundings. Worse, the daemon's substrate, the physical system that stores 10 to the 80 bits, has a mass. That mass contributes to the gravitational field, and there is a limit, called the Bekenstein bound, on how much information can be stored in a region of space of a given size and energy. The bound is S is less than or equal to 2 pi KRE over h bar c, where r is the radius and E is the energy. For a region the size of the observable universe, with the energy density we measure, the Bekenstein bound permits roughly 10 to the 120 bits. That sounds like plenty, 10 to the 80 particles times a few bits each, but only if the daemon is the size of the universe. A daemon smaller than the universe cannot store the state of the universe. A daemon the size of the universe has nowhere to dissipate its waste heat. The calculation collapses under its own thermodynamic weight. Hans Bremermann, in 1962, derived a different limit, the maximum rate at which any physical system can process information. Bremermann's limit is c squared over h, roughly 1.36 times 10 to the 50th bits per second per kilogram, where c is the speed of light and h is Planck's constant. This limit arises from quantum mechanics and relativity. A kilogram of matter, converted entirely to energy and used to flip bits, cannot flip them faster than Bremermann's limit. The observable universe has a mass of about 10 to the 53 kilograms and an age of about 10 to the 17 seconds. Multiply those numbers by Bremermann's limit, and you get an upper bound on the total number of bit operations the universe could have performed since the Big Bang, roughly 10 to the 120. That is the same order of magnitude as the Bekenstein bound. The universe does not have enough time or enough matter to compute its own next state, let alone predict its distant future. A related limit is the Margulis-Levitin bound, which says that a system with energy E can perform at most 6 times 10 to the 33 operations per second per joule. These are not engineering limits. They are limits imposed by the laws of physics. No clever algorithm, no advanced technology can overcome them. They place a ceiling on what any physical system, demon included, can compute. Think of it this way. You hire an accountant to balance the books of every company on Earth. The accountant is fast, meticulous, never sleeps. But there are 10 million companies, each with 10,000 transactions per day. The accountant can process 1 transaction per second. After 1 day, the accountant is 100 billion transactions behind and falling further every moment. The backlog grows faster than the accountant can work. No matter how fast the accountant becomes, the problem scales faster. The demon faces the same bind. The universe generates new states faster than the demon can track them, because the demon is part of the universe. It cannot run the calculation without becoming the calculation. Maxwell's demon, introduced by James Clerk Maxwell in 1867, was a different thought experiment, but a related one. Picture a box divided by a partition with a small door. Gas molecules bounce around on both sides. The demon watches the molecules and operates the door, letting fast molecules pass from left to right and slow molecules from right to left. Over time, the right side heats up and the left side cools down, decreasing the entropy of the system without doing macroscopic work. This seems to violate the second law of thermodynamics. The resolution, worked out by Leo Szilard, Léon Brillouin and Landauer, is that the demon must store information about which molecules are fast and which are slow. To avoid filling its memory indefinitely, it must eventually erase that information. The erasure dissipates heat, exactly compensating the entropy decrease caused by the sorting. Maxwell's demon does not violate the second law. It hides the cost in the act of forgetting. Laplace's demon faces the same problem. To predict the future, it must measure the present. To measure the present, it must interact with the particles, disturbing them. To store the measurements, it must allocate memory. To update the memory, it must erase old data. Every step costs energy. The demon is not a passive observer. It is an active participant, and its participation carries thermodynamic consequences. Even in a deterministic universe, the demon cannot extract that determinism without altering the system it seeks to predict. There is a deeper point here. Information is not separate from physics. A bit is a physical thing, encoded in the orientation of a spin, the charge on a capacitor, the polarization of a photon. Reading a bit, copying a bit, erasing a bit, all of these are physical processes governed by the same laws as any other. The demon is not above the universe looking down. It sits inside the universe, made of the same particles, obeying the same constraints. And those constraints are not gentle suggestions. They are hard limits written into the fabric of spacetime and quantum mechanics. At this point, chaos and thermodynamics have killed Laplace's demon twice. Chaos shows that perfect knowledge of the initial state is impossible to maintain. Thermodynamics shows that even if the demon somehow acquired perfect knowledge, it could not compute fast enough, or store enough data, or dissipate enough heat to predict the future. The daemon is blocked by sensitivity to initial conditions and by the physical limits of information processing. But there is a third death, subtler and more contentious. Quantum mechanics entered physics in the early 20th century, and it introduced a form of unpredictability that comes neither from chaos nor from ignorance. In the standard interpretation, quantum systems do not possess definite properties until they are measured. Before measurement, an electron does not have a position. It has a wave function, a mathematical object that assigns probabilities to different outcomes. Measure the position and the wave function collapses, and the electron is found at one location. The outcome is probabilistic. Run the same experiment many times with identically prepared electrons and you get a distribution of results. The most common interpretation, descended from Niels Bohr and the Copenhagen school, says this is not because of hidden variables or insufficient precision. It is because the electron genuinely did not have a position until you forced it to choose one. The Heisenberg uncertainty principle, formulated in 1927, quantifies this. Delta x times delta p is greater than or equal to h bar over 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck constant. This is not a limit on measurement precision. It is a limit on the definiteness of the properties themselves. You cannot prepare a particle with a sharply defined position and a sharply defined momentum. The more precisely you know where it is, the less precisely you can know how fast it is moving. This is not ignorance in the sense of chaos. It is indeterminacy in the structure of reality. Or so the standard interpretation claims. The question of whether quantum randomness is fundamental or merely apparent, whether there is a deeper deterministic layer beneath the probabilities, has been debated for a century. And the experiments that seem to settle it rank among the most carefully constructed in the history of science. In 1964, John Stuart Bell, a physicist at CERN, proved a theorem that would eventually dismantle the most intuitive picture of quantum mechanics. Bell wanted to know whether quantum mechanics is complete, whether the probabilities it gives are fundamental, or whether there might be hidden variables, additional information that determines the outcome but stays inaccessible to us. Albert Einstein, along with Boris Podolsky and Nathan Rosen, had argued in 1935 that quantum mechanics must be incomplete. They pointed to entanglement, a phenomenon where two particles are correlated in a way that seems to require faster-than-light influence if the correlations are to be explained by local hidden variables. Bell showed that any theory based on local hidden variables, variables that travel no faster than light and determine the outcome of measurements, must satisfy certain inequalities when you measure correlations between entangled particles. Quantum mechanics predicts violations of those inequalities. If the violations are observed, local hidden variables are ruled out. Either the variables are non-local, allowing faster-than-light influence, or there are no hidden variables at all and the randomness is fundamental. The most widely used version is the Clauser-Horn-Shimony-Holt inequality, published in 1969. You create pairs of entangled particles and send them to two detectors separated in space. Each detector has a setting, chosen by the experimenter, that determines what property of the particle is measured. You record whether the particle is detected or not. and you compute correlations between the two detectors. The CH-SH inequality says that a certain combination of correlations, denoted S, must satisfy the absolute value of S is less than or equal to 2 if the world is governed by local realism, the idea that particles have definite properties independent of measurement, and that influences travel no faster than light. Quantum mechanics allows S to reach roughly 2.828, the square root of 2 times 2, a bound proved by Boris Tsilson. Experiments have consistently measured S near the quantum limit, violating the CH-SH inequality. For decades, though, the experiments had loopholes, ways a local hidden variable theory could, in principle, mimic quantum mechanics by exploiting imperfections in the setup. The detection loophole opens if detectors are inefficient, missing some particles. A hidden variable theory could postulate that only certain particles are detected, biasing the results. The locality loophole opens if the detectors sit close enough that a signal could pass between them at the speed of light during the measurement, coordinating the outcomes. A complete test requires closing both loopholes simultaneously. In 2015, 3 experiments achieved this. The first, led by Ronald Hansen at Delft University of Technology, used electron spins in nitrogen vacancy centers in diamond, separated by 1.3 kilometers. The entanglement was distributed using photons, and the measurement was fast enough that no light-speed signal could travel between the detectors. The detection efficiency ran high enough to close the detection loophole. They measured S equal to 2.42, with a p-value of 0.039, violating the bound of 2. The result appeared in Nature in October 2015. 2 other groups reported similar results within weeks. A team at the National Institute of Standards and Technology in Boulder used photons and achieved an S value that strongly violated local realism. A group in Vienna, led by Anton Zeilinger, used a different photonic setup and closed both loopholes with a different combination of techniques. The 3 papers together are considered the gold standard, loophole-free violations of Bell's theorem. Local realism, as a description of nature, is ruled out by these experiments. But consider what that means. Local realism is the conjunction of 2 assumptions: realism, that particles have definite properties independent of measurement, and locality, that no influence travels faster than light. Violating the conjunction means at least one of those assumptions is false. The mainstream interpretation drops realism. Particles do not have definite properties until measured. The wave function is not a description of a hidden reality, but a tool for computing probabilities. A minority drops locality, allowing faster-than-light correlations, though not faster-than-light signaling, which remains forbidden. And a smaller minority rejects neither, instead challenging a third, quieter assumption built into Bell's theorem: statistical independence. Statistical independence is the assumption that the hidden variables carried by the particles are uncorrelated with the measurement settings chosen by the experimenters. In symbols, if lambda represents the hidden variables and A and B represent the settings at the 2 detectors, then the probability distribution of lambda, given A and B, is the same as the distribution of lambda alone. Bell's theorem requires this. If statistical independence is violated, if the hidden variables and the settings are correlated, then a local hidden variable theory can reproduce the quantum predictions without faster-than-light influence. This is called superdeterminism. The name misleads. It does not mean more deterministic than determinism. It means that the experimenter's choice of settings is not independent of the system being measured. Both the settings and the hidden variables are determined by earlier events, and those earlier events impose correlations that persist into the experiment. In this view, the free choice of the experimenter is illusory. The choice is fixed by the prior state of the universe, including the particles that will later be measured. Superdeterminism has a reputation for being conspiratorial. Critics say it requires the universe to know in advance what settings the experimenter will choose and to arrange the hidden variables accordingly, a kind of cosmic conspiracy to simulate quantum mechanics. But proponents, notably Gerard de Hooft and Sabine Hossenfelder, argue that this mischaracterizes the position. In a deterministic universe, every event is fixed by the initial conditions. There is no conspiracy, only causality. The correlation between settings and hidden variables arises naturally from a common causal past. In the same way that the temperature of your coffee and the temperature of the room are correlated because they share a thermal history. Gerard de Hooft, a Dutch physicist who shared the Nobel Prize in 1999 for work on the electro-weak interaction, has spent decades developing a program he calls the cellular automaton interpretation of quantum mechanics. The idea holds that at the Planck scale, 1.616 times 10 to the minus 35 meters, the smallest length that makes sense in current physics, the universe is a deterministic system, something like a cellular automaton. Ontological states, the real states of the system, evolve by strict rules, permutations of a discrete set of possibilities. Quantum mechanics in this picture is not fundamental. It is a tool for describing systems when you lack complete information about the ontological states. The wave function is a bookkeeping device, not a real object. In 2016, 't Hooft published a book-length monograph laying out this interpretation. He writes, "Quantum mechanics is looked upon as a tool, not as a theory. The quantum formalism works because it correctly captures the statistical behavior of the underlying deterministic system, averaged over all the ontological details we cannot track. Superposition is not a particle being in multiple states at once. It is our ignorance of which ontological state the particle occupies. Measurement does not collapse a wave function. It reveals information about the ontological state that was determined long before the measurement." 't Hooft is careful to admit the limitations of this program. He writes, "Having said all this, I do admit that what we have is still only a theory. It can and will be criticized and attacked, as it already was. I know that some readers will not be convinced. The models he has built are either too simple, which means they do not describe interesting interacting particles, or they seem to exhibit more subtle defects. Specifically, he has not produced a fully Lorenz invariant second quantized theory of interacting particles starting from a deterministic substrate. The project is unfinished. But 't Hooft argues that the absence of a complete theory does not mean the approach is wrong. It means more work is needed. In 2020, Sabine Hossenfelder and Tim Palmer published a paper titled Rethinking Superdeterminism. They define a superdeterministic theory as one that is deterministic, treats the quantum state as epistemic rather than ontological, violates statistical independence, but respects what they call continuity of action, a local relativistic causality where influences propagate smoothly. They argue that the objections to superdeterminism rest on intuitions formed in classical linear systems, and that those intuitions mislead us in the quantum domain. One common objection is the free will objection. Superdeterminism denies that experimenters can freely choose measurement settings. Hossenfelder and Palmer respond that free choice is a label that anthropomorphizes a mathematical assumption. Whether humans have free will in the philosophical sense is irrelevant. The question is whether, in a physical theory, the experimenter's choice of settings is correlated with the properties of the system being measured. In a deterministic universe, everything is correlated with everything else through the initial conditions. The word choice does not change that. Another objection is fine-tuning. If the hidden variables must be correlated with the settings in just the right way to reproduce the quantum predictions, that seems like an implausible coincidence. Hossenfelder and Palmer argue that this is not fine-tuning in the problematic sense. It is simply the statement that the universe has a particular set of initial conditions. Every deterministic theory requires initial conditions. Superdeterminism specifies that those conditions include correlations that, when propagated forward by deterministic laws, produce the appearance of quantum randomness. They write, "These approaches, needless to say, are still in their infancy. They leave open many questions, and it might well turn out that none of them is the right answer. But they insist that the approach is worth pursuing, and that dismissing it on grounds of conspiracy or implausibility is premature." The debate over superdeterminism is not settled. Critics point out that no superdeterministic model has yet made a testable prediction that differs from quantum mechanics. If the theory is empirically indistinguishable from the standard interpretation, some argue it should be rejected on grounds of parsimony. Proponents counter that parsimony is not the only virtue. A deterministic, realist ontology is conceptually simpler than a probabilistic, observer-dependent one, even if the two make identical predictions. In 2017, a team led by Anton Zeilinger performed a variation of the Bell test that pushed the freedom of choice loophole further back in time. Instead of using random number generators to choose the detector settings, they used the color of light from stars in the Milky Way. Photons from two stars, separated by large angles on the sky, arrived at a telescope in Vienna. The wavelength of each photon, whether it was redder or bluer than a chosen threshold, determined the setting of one of the two detectors measuring entangled photon pairs on Earth. The light from those stars had been traveling for hundreds of years. Any mechanism that correlated the hidden variables of the entangled photons with the detector settings would have had to operate at least that long ago, when the starlight was emitted. They measured S equal to 2.65 plus or minus 0.02, violating the local realist bound of 2. The result appeared in Physical Review Letters in February 2017. The implication runs like this. If superdeterminism is correct, the correlation between the photon's hidden variables and the Milky Way starlight must have been established at least hundreds of years ago. In 2018, the same team extended the test using light from quasars, distant luminous objects powered by supermassive black holes. The quasars they selected had redshifts corresponding to distances such that their light was emitted 7.8 and 12.2 billion years ago, when the universe was young. The color of the quasar light set the detector angles for entangled photons generated on Earth. The experiment ran simultaneously at 2 telescopes. The William Herschel telescope on La Palma in the Canary Islands and the Telescopio Nazionale Galileo nearby, with additional real-time measurement in Vienna. The detectors measuring the entangled photons were separated enough to ensure that no light-speed signal could coordinate the outcomes during the measurement. The result again violated the CHSH inequality, ruling out local hidden variables, unless those variables were correlated with the measurement settings at least 7.8 billion years ago. The paper states that this excludes such correlations from 96% of the spacetime volume of the past light cone of the experiment. Any local realist mechanism that knew what settings would be chosen had to begin its operation when the universe was less than a quarter of its current age. Alan Guth, one of the co-authors and the physicist who proposed cosmic inflation in the early 1980s, said in an MIT press release, "If some conspiracy is happening to simulate quantum mechanics by a mechanism that is actually classical, that mechanism would have had to begin its operations somehow knowing exactly when, where, and how this experiment was going to be done, at least 7.8 billion years ago. That seems incredibly implausible. So we have very strong evidence that quantum mechanics is the right explanation." He added, "We certainly made it unbelievably implausible that a local realistic theory could be underlying the physics of the universe." But notice what is not claimed. Guth calls the conspiracy incredibly implausible, but he does not say it is impossible. The 4% of the past light cone that remains unexcluded includes the earliest moments of the universe, the Big Bang itself among them. A superdeterministic correlation established at the very beginning in the initial conditions of space-time would not need to know the experiment in advance. It would simply be present in the structure from which everything else unfolds. The quasar experiment pushes the loophole back to the origin of time, but it cannot close it there. If the future is fixed in the geometry of the block universe, then the quasar light and the detector settings and the hidden variables are all part of the same 4-dimensional pattern, none prior to the others in any absolute sense, all written into the space-time manifold together. The block universe is the idea that time is a dimension like space, and that past, present, and future all exist with equal reality. You experience time as flow, as a moving present that leaves the past behind and approaches a future not yet real. But relativity suggests this picture is wrong. In special relativity, observers in relative motion disagree about which events are simultaneous. Two people passing on a sidewalk can disagree by days about what is happening right now in the Andromeda galaxy, 2.5 million light-years away. If simultaneity is relative, if there is no observer-independent fact about which distant events are occurring now, then the distinction between past, present and future cannot be fundamental. All events are equally real, laid out in a four-dimensional space-time. You move through that space-time along your world line, experiencing events in sequence. But the events themselves do not come into being as you reach them. They are already there. This is sometimes called eternalism. It is the majority view among physicists who work in relativity, though many are uncomfortable with its implications for free will and the flow of time. If the future already exists, in what sense is it undecided? If your world line is a fixed curve through space-time, connecting your birth to your death, how can your choices change anything? The standard answer holds that your choices are part of the fixed structure. You do not stand outside space-time choosing which world line to trace. You are the world line. The experience of deliberation, of weighing options and selecting one, is real, but it is also determined. The choice you will make is already a feature of the geometry, as much a part of space-time as the curvature around a massive star. Quantum mechanics complicates this picture. The Schrödinger equation, I times h bar times the partial derivative of psi with respect to time equals the Hamiltonian operator acting on psi, describes how the wave function evolves. This evolution is smooth, deterministic, and reversible. Know the wave function at one time, and you can calculate it at any other time, forward or backward. But measurement seems to break that determinism. The wave function does not evolve into a definite outcome. It collapses into one, chosen probabilistically according to the Born rule. The probability of an outcome is the squared magnitude of the wave function's amplitude for that outcome. The source of this probability is a genuine mystery. The electron appears here and not there, even though the wave function assigned non-zero amplitude to both. And nothing in the formalism explains the selection. The measurement problem is the question of what happens during a measurement. The Copenhagen interpretation, as articulated by Niels Bohr, treats measurement as a primitive process that lies outside the quantum formalism. The world is divided into a quantum system and a classical measuring apparatus. The system obeys quantum mechanics. The apparatus does not. When the two interact, the wave function collapses and a classical outcome is recorded. But this division is arbitrary. The apparatus is made of particles that themselves obey quantum mechanics. The reason those particles behave classically is unclear, and so is the location of the boundary between the quantum system and the classical world. Decoherence offers a partial answer. When a quantum system interacts with a large environment, air molecules, photons, thermal radiation, system and the environment become entangled. Information about the system leaks into the environment, and the coherent superposition that defined the quantum state is destroyed. What remains is a statistical mixture that looks, for all practical purposes, like a classical probability distribution. The system behaves as though it has a definite state, even though the full quantum description is still a superposition. Wojciech Zurek, a physicist at Los Alamos, has developed this idea into a framework called quantum Darwinism. The environment does not just decohere the system, it redundantly copies information about certain properties of the system into many environmental degrees of freedom. Those properties, called pointer states, are the ones that survive the interaction with the environment and can be measured by multiple observers. This redundancy explains why we all agree on what we see. When you measure the position of a dust grain, you are not collapsing a wave function in some mysterious way. You are reading information that has already been broadcast into the photons bouncing off the grain, into the air molecules colliding with it, into the electromagnetic field around it. The information is public, accessible to anyone with a detector. Experimental tests of quantum Darwinism began in the 2000s. In 2019, a team led by Tullio de Lima and David Vitali used nitrogen vacancy centers in diamond to show that information about a central spin is redundantly encoded in the surrounding nuclear spins, allowing multiple observers to extract the same information without disturbing the central system. Another group, led by Jianwei Pan in China, used photonic cluster states to demonstrate that classical information emerges from quantum correlations through environmental interactions. In 2025, a team at the University of Science and Technology of China used superconducting circuits to observe quantum Darwinism in a highly controlled system, showing how the environment selects pointer states and replicates information about them. Decoherence and quantum Darwinism explain how the appearance of classicality arises, but they do not explain the collapse itself. They do not tell you why, when you look at the dust grain, you see it in one location rather than a superposition of many. Decoherence destroys the interference between different outcomes, making them effectively independent. But it does not select which outcome occurs. For that, you still need the Born rule. And the Born rule is a postulate, not derived from anything deeper within standard quantum mechanics. It tells you the probabilities, but it does not tell you why probability enters at all. One interpretation that eliminates collapse is the many worlds interpretation, introduced by Hugh Everett in 1957. In this view, the wave function never collapses. The Schrödinger equation holds universally, including during measurements. When you measure a quantum system, you and the system become entangled. The wave function of the combined system branches into multiple terms, each corresponding to a different outcome. In one branch, you see the electron on the left. In another, you see it on the right. Both branches are real, but they no longer interact. You experience one outcome not because the others did not happen, but because you are in one branch and cannot access the others. Many worlds preserves determinism. The universal wave function evolves smoothly, with no randomness. The appearance of randomness arises because you, the observer, do not know which branch you are in until after the measurement. From the perspective of the universal wave function, all outcomes occur. From your perspective, inside one branch, it looks as though the universe made a random choice. The randomness is indexical, a fact about your location in the branching structure, not a fact about the structure itself. Critics of many worlds argue that it has a problem with probability. If all outcomes happen, why do some feel more likely than others? Why does the electron appear on the left 75% of the time rather than 50% or 25%? The Born rule assigns probabilities to outcomes, but in a theory where all outcomes are real, the meaning of probability becomes obscure. Proponents have offered various answers, often invoking decision theory or rational betting behavior, but the question remains contentious. Another interpretation, more radical, denies that the quantum state represents reality at all. This is cubism, short for quantum Bayesianism, developed by Carlton Caves, Christopher Fuchs, and Rudiger Schack. In this view, the wave function is not a description of the world, it is a description of an agent's beliefs about what they will observe. Probabilities are not features of the system, they are degrees of belief held by the agent. Measurement does not reveal a pre-existing property, it updates the agent's information. Two agents with different information can assign different wave functions to the same system, and both are correct because the wave function is personal. Cubism dissolves the measurement problem by denying that there is an objective wave function to collapse. It also dissolves the paradoxes of entanglement and non-locality, because those paradoxes arise from treating the wave function as a description of something independent of observers. If the wave function is just a tool for agents to organize their expectations, there is no mystery in the fact that agents in different situations use different tools. But cubism is anti-realist. It does not tell you what the world is, only how agents should think about their experiences. For physicists who believe science should describe reality, not just subjective beliefs, cubism is unsatisfying. A different direction is to modify quantum mechanics rather than reinterpret it. Objective collapse models, such as the Girardi-Rimini-Weber model and continuous spontaneous localization, propose that the wave function undergoes spontaneous, random collapses at a low rate, independent of measurement. For microscopic systems, the collapse rate is negligible, and quantum mechanics holds. For macroscopic systems with many particles, the collapse rate accumulates, and the system is quickly driven into a definite state. This explains why we do not see macroscopic superpositions. The collapse is a real physical process, governed by modified equations that include stochastic terms. These models make testable predictions. They predict a tiny amount of heating, a diffusion of energy into the system due to the collapse mechanism. experiments have increasingly constrained the parameter space of objective collapse models. Interferometry experiments with ever larger molecules, tests of gravitational effects on quantum systems, and precision measurements of spontaneous radiation all place limits on how strong the collapse can be. The models are not yet ruled out, but they are squeezed into a narrower and narrower corner. What all of these interpretations share is an attempt to make sense of quantum mechanics as it stands. But there is another possibility, that quantum mechanics is not the final theory. That beneath the probabilities and the wave functions lies a deeper layer, deterministic and perhaps even classical in structure, that we have not yet uncovered. Gerard 't Hooft's cellular automaton interpretation is one example. Superdeterminism is another. A third is retrocausality. Retrocausality is the idea that future events can influence the past. In a retrocausal theory, the quantum state of a system at a given time is determined not only by the past, but also by the future. This is the core of the two-state vector formalism, developed by Yakir Aharonov, Peter Bergman, and Joel Leibovitz in 1964, and later expanded by Aharonov and Lev Weidman. A quantum system at time t is described by two state vectors: a forward-evolving state from the past, prepared by some initial condition, and a backward-evolving state from the future, fixed by a later measurement or boundary condition. The complete description is the overlap of the two. The present is sandwiched between past and future. This formalism leads to surprising predictions. It allows for weak measurements introduced by Aharonov, David Albert and Weidman in 1988, where you measure a property of a quantum system with minimal disturbance. The result of a weak measurement is the weak value, which can lie outside the range of possible eigenvalues for that observable. If a spin can be either up or down, the weak value of the spin, given certain pre- and post-selections, can be 3. This is not an error. It is a feature of the two-state vector formalism. The weak value is a kind of conditional expectation, weighted by both the past and the future. Aharonov and Weidman write that a system is described completely by a two-state vector, which consists of a quantum state defined by the results of measurements performed on the system in the past relative to the time t, and of a backward-evolving quantum state defined by the results of measurements performed on this system after the time t. They note that the results of measurements in the future are only partially constrained by the results of measurements in the past. Thus, the concept of a quantum state is genuinely time asymmetric. But the two-state vector formalism can also be read as a time-symmetric ontology. If both past and future are real, if the quantum state at the present is jointly determined by boundary conditions at both ends of time, then causality is not a one-way street. The future influences the present just as the past does. Hugh Price, a philosopher at Cambridge, has argued that any time-symmetric interpretation of quantum mechanics that treats the quantum state as real must be retrocausal. The standard interpretation treats the past as fixed and the future as open. But that asymmetry is not demanded by the equations. The Schrödinger equation is time-symmetric. Run it backward and it works just as well. The asymmetry in our experience of time, the sense that the past is fixed and the future is not, may be a feature of our thermodynamic embedding in a universe with a low entropy past, not a feature of the fundamental laws. Ken Wharton, a physicist at San Jose State University, has developed retrocausal models that reproduce the quantum predictions while preserving locality. The key is to allow correlations between events that are not explained by a common past cause, but by a common future effect. Two entangled particles are correlated not because they were prepared together and carried that correlation forward, but because their futures are constrained by a later boundary condition, and that constraint propagates backward to produce the observed correlation. This sounds bizarre, yet it is mathematically consistent, and it avoids the non-locality that Bell's theorem seems to force. Matthew Leifer and Matthew Pusey, in a 2016 paper, challenged Price's argument, showing that a time-symmetric interpretation can avoid retrocausality if you replace the assumption of realism with a different assumption they call lambda mediation. But the debate continues. Emily Adlam, in a 2022 paper titled Two Roads to Retrocausality, argues that there are multiple routes to a retrocausal interpretation, and that the approach deserves more attention than it receives. The problem with retrocausality, from an empirical standpoint, is that it does not make predictions that differ from standard quantum mechanics. It reinterprets the same data. The violation of Bell's inequality can be explained by backward influence from the measurement settings to the hidden variables, rather than by fundamental randomness or non-local correlations. But the violation itself is the same. This makes retrocausality hard to test. It offers a different story about what is happening, while the observable outcomes stay unchanged. One way to test retrocausality would be to look for situations where the future boundary condition is manipulated and the past behavior changes accordingly. But manipulating the future in a controlled way, then checking the past to see if it responded, runs into a wall. The future has not happened yet from your perspective. By the time you set the future boundary condition, the past event is already in your history. This is the difficulty of testing a time-symmetric theory in a universe where you experience time as one-directional. There is another, more recent challenge to the standard interpretation. In 2018, Daniela Fraukiger and Renato Renner at ETH Zurich published a thought experiment that shows quantum mechanics, applied consistently to observers who themselves use quantum mechanics, leads to contradictory conclusions. The scenario involves nested measurements. An agent measures a quantum system, and then another agent measures the first agent, treating the agent and the system together as a larger quantum system. Each agent, reasoning within quantum mechanics, can assign a definite outcome to their own measurement. But when one agent tries to predict what another agent will observe, the predictions can be mutually inconsistent. One agent concludes with certainty that a particular outcome occurred, while another agent concludes with certainty that a different outcome occurred. And both conclusions are derived from applying the standard rules of quantum mechanics. The paper's title is "Quantum Theory Cannot Consistently Describe the Use of Itself." Frauschiger and Renner write that the agent's conclusions, although all derived within quantum theory, are thus inconsistent. This suggests that quantum mechanics, when extended to agents who are themselves quantum systems, does not support a single, objective account of what happens. Different agents have different facts, and those facts can contradict each other. This is not a matter of ignorance or limited information. It is a structural feature of the theory. One response to Frauschiger-Renner is to deny that there is an objective, observer-independent reality. This is the cubist move. Each agent has their own quantum state, and there is no global fact of the matter about what is true. Another response is to adopt many worlds. The agents are in different branches, so their contradictory conclusions are both correct, just not in the same branch. A third response is to modify quantum mechanics in a way that restores consistency, perhaps by introducing objective collapse, or by imposing a boundary between quantum and classical systems that cannot be crossed. In 2020, a team led by Kok-Wei Bong, working with Howard Wiseman and others at Griffith University in Australia, performed an experimental test related to Frauschiger-Renner. They used photonic systems to implement a version of Wigner's friend, a thought experiment where a friend measures a quantum system inside a lab, and Wigner, outside the lab, treats the entire lab as a quantum system and performs a measurement on it. The experiment tested an inequality called local friendliness, which combines two assumptions: absoluteness of observed events, meaning that a measurement outcome is a fact independent of who observes it, and local agency, meaning that an agent's choice of measurement is independent of the system being measured. The experiment violated the local friendliness inequality, showing that quantum correlations are incompatible with both assumptions holding simultaneously. Either observed events are not absolute, and different observers can hold incompatible but equally valid facts, or local agency is violated, and the agent's choice is correlated with the system in a way that undermines independence. This is a stronger constraint than Bell's theorem. Bell rules out local realism. Local friendliness rules out a combination of observer-independent facts and local free choice. The experiment pushes the conceptual crisis deeper. Another set of experiments tests macro-realism, the idea that macroscopic objects are always in definite states, even when not observed. The Leggett-Garg inequalities, proposed by Anthony Leggett and Anupam Garg in 1985, are the temporal analogue of Bell's inequalities. Instead of correlations between spatially separated measurements, they involve correlations between measurements at different times on the same system. If the system is macroscopic and realistic, always in a definite state, and measurements do not disturb future states, then certain combinations of time correlations cannot exceed a bound. Quantum mechanics violates that bound. In 2024, a team at the Institut Laue-Langevin in Grenoble used neutron interferometry to perform a loophole-free Leggett-Garg test. They measured a quantity called K, defined as the sum of 3 time correlations between measurements at successive times. Macro-realism requires K to be less than or equal to 1. They measured K equal to 1.120 plus or minus 0.007, violating the bound by more than 17 standard deviations. The measurement used ideal negative measurements, a technique where you confirm that a system is not in a certain state without directly probing what state it is in. This closes a loophole related to invasiveness. The result shows that even for relatively large quantum systems, and neutrons are composite particles made of quarks, the assumption that the system is always in a definite state, undisturbed by measurement, does not hold. Similar tests have been performed with photons, superconducting circuits, and even mechanical oscillators. Each pushes the boundary of macro-realism further. The quantum classical divide, if it exists, is not where intuition suggests. Objects that seem macroscopic enough to have definite properties at all times, big enough, heavy enough, warm enough, still exhibit quantum behavior under the right conditions. One final concept that ties into the group question of randomness is algorithmic randomness, developed in the 1960s by Andrei Kolmogorov, Gregory Chaitin, Ray Solomonoff, and others. A sequence of bits is algorithmically random if the shortest computer program that produces the sequence is as long as the sequence itself. The sequence is incompressible. It has no pattern that a shorter description can capture. This is a rigorous mathematical definition of randomness. It does not rely on physical processes. It is a property of the sequence as an abstract object. Per Martin-Löf extended this definition to infinite sequences, introducing a notion of randomness based on measure theory. A sequence is Martin-Löf random if it passes all effectively computable statistical tests. Any pattern you can write an algorithm to detect, the sequence will not exhibit. This is a strong condition. Most sequences are random in this sense, but only because there are so many sequences. Any particular sequence that you actually encounter in nature or in a computation requires justification before you can call it random. Now consider a deterministic system like the Lorenz attractor. It produces trajectories that look random. Sample the trajectory at regular intervals and record the sign of one of the coordinates, and you get a sequence of bits that appears random. Statistical tests will not distinguish it from a coin flip, assuming the sampling is done properly. But the sequence is not Martin-Löf random, because there is a short program, the Lorenz equations and the initial condition, that produces it. The sequence is compressible in principle, even if it is incompressible in practice, given limited computational resources. This raises a subtle question. When you measure the outcome of a quantum event, are you accessing a sequence that is Martin-Löf random, or is the appearance of randomness due to practical incompressibility of an underlying deterministic process? If the universe is a cellular automaton running at the Planck scale, The sequence of quantum outcomes is determined by the initial state and the update rule. The sequence is compressible, since the program is the automaton. But if the automaton is complex enough, and you do not have access to its state, the outcomes look random to you. Randomness becomes an epistemic category, not an ontological one. It describes your relation to the data, not the data's relation to reality. A related idea appears in the work of Millet Gu, a physicist at Nanyang Technological University in Singapore. Gu and collaborators have studied the memory requirements for simulating stochastic processes using quantum systems versus classical systems. Classical models of a random process require a certain amount of memory, quantified by a measure called statistical complexity. This is the information you must store about the past in order to predict the future. For some processes, quantum systems can simulate the same output with strictly less memory than any classical system. The quantum memory advantage has been demonstrated experimentally using photonic processors. The implication is striking. The amount of randomness you attribute to a process depends on the model you use. A sequence that requires 10 bits of memory to simulate classically might require only 3 bits if you use a quantum computer. The randomness is not intrinsic to the sequence. It is a function of the computational resources available to compress and predict it. This does not prove that quantum randomness is epistemic, but it shows that the boundary between determinism and randomness is blurred by computational considerations. There is a parallel in statistical mechanics. The second law of thermodynamics says that entropy increases. A gas in a box, initially confined to one corner, will spread out and never spontaneously return to the corner. This looks like an arrow of time, an irreversible process. But the microscopic laws governing the gas molecules are time-symmetric. Reverse the velocity of every molecule, and the gas would contract back into the corner. The increase in entropy is not a feature of the laws. It is a feature of the initial condition. The gas started in a low entropy state, and of the fact that we coarse grain, averaging over microscopic details we cannot track. The Wilsonian renormalization group, developed by Kenneth Wilson in the 1970s, formalizes this coarse graining. You define a theory at a microscopic scale, with many degrees of freedom. Then you integrate out the short-distance fluctuations, averaging over them to obtain an effective theory at a larger scale. The effective theory has fewer degrees of freedom and different coupling constants. As you increase the scale, the theory flows under the renormalization group transformations. Some details wash out, others become important. The renormalization group tells you how microscopic complexity gives rise to macroscopic simplicity. The relevance to randomness runs like this. A microscopic theory might be deterministic, with every degree of freedom evolving by strict rules. But when you coarse grain, averaging over the degrees of freedom you cannot resolve, the effective theory at the macroscopic scale looks stochastic. The average dynamics include noise terms that represent the influence of the unresolved microscopic variables. This noise is not fundamental. It is an artifact of the averaging. But from the perspective of an observer who works only at the macroscopic scale, the noise is real and unpredictable. The randomness is emergent. In a cellular automaton, the state is a grid of cells, each in a discrete state. The update rule is a function that takes the state of a cell and its neighbors at time t and outputs the state of that cell at time t+1. The rule is deterministic, but the global pattern produced by iterating the rule can grow extraordinarily complex, exhibiting structures that grow, collide, and decay in ways that resist simple description. Some cellular automata are capable of universal computation, meaning they can simulate any algorithm, including algorithms that generate random-looking sequences. The randomness is baked into the initial condition or the rule itself, encoded in the deterministic structure, not introduced from outside. Gerard 't Hooft conjectures that the universe is a cellular automaton at the Planck scale. Quantum mechanics is the coarse-grained description that emerges when you average over the ontological states you cannot access. The wave function is a bookkeeping tool for tracking the probabilities of different ontological configurations given incomplete information. Measurement does not collapse the wave function in any physical sense. It updates your information about which ontological state you are in. The Born rule arises statistically from the distribution of ontological states weighted by the cellular automaton's dynamics. This is speculative. 't Hooft acknowledges that his models are not yet complete, but the idea is not absurd. It draws on well-established concepts: coarse graining, renormalization, information theory, and the fact that deterministic systems can produce complex, apparently random behavior. If the program succeeds, it would dissolve the quantum measurement problem, explain the Born rule, and restore a deterministic, realist ontology to physics. If it fails, it will fail by running into a mathematical obstruction, an inability to reproduce the quantum predictions, or a violation of relativity, not by being conceptually incoherent. John Conway and Simon Cochen, in their free will theorem, published in 2006 and strengthened in 2009, argue the opposite. They prove that if experimenters have a certain kind of freedom to choose measurement settings, not free will in the philosophical sense, but freedom in the sense that the choice is not determined by events in the past, light cone of the choice, then the particles being measured must also possess that same freedom. The response of the particle is not determined by the entire previous history of the universe. Their axioms are spin, which says that certain spin-1 measurements exhibit a particular correlation pattern, twin, which says entangled particles exhibit the expected quantum correlations, and MIN, which replaces an earlier assumption about finite speed with a statement about the independence of measurement choices at space-like separated locations. Conway and Cochen write, "If indeed we humans have free will, then elementary particles already have their own small share of this valuable commodity. More precisely, if the experimenter can freely choose the directions in which to orient his apparatus in a certain measurement, then the particle's response is not determined by the entire previous history of the universe." This is a direct challenge to superdeterminism. The theorem assumes that experimenters can make choices that are not fixed by the past. Superdeterminism denies that assumption. The theorem and superdeterminism are logically incompatible. One or the other must be false. The free will theorem has been criticized on various grounds. Some argue that the MIN axiom smuggles in a strong assumption about independence that is not experimentally verified. Others point out that the theorem does not rule out determinism. It rules out determinism combined with the independence of measurement choices. Give up independence and the theorem does not apply. But the theorem stands as a rigorous piece of mathematics, showing that within a certain framework, genuine indeterminism at the particle level is implied by experimenter freedom. This is the crux. Superdeterminism says there is no experimenter freedom, and the choice is fixed by prior causes, including causes shared with the particles. The free will theorem says that if there is experimenter freedom, the particles are indeterministic. The two positions are mirror images. Each buys something at a cost. Superdeterminism buys determinism and realism at the cost of independence. The free will theorem buys independence at the cost of determinism. The data do not choose between them. In 2018, Latham Boyle, Kieran Finn and Neil Turok at the Perimeter Institute proposed a cosmological model that is explicitly time-symmetric. They argue that the universe did not begin at the Big Bang in the usual sense. Instead, the Big Bang is a mirror, and the universe before the Big Bang is the CPT symmetric image of the universe after it. CPT stands for charge conjugation, parity inversion, and time reversal. Three symmetries that, combined, are believed to be exact in all fundamental theories. In the Boyle-Finn-Turok model, the universe and its CPT mirror form a pair, emerging together from a state of maximal symmetry. Time runs forward in our universe and backward in the mirror universe, but both are equally real. This model makes predictions. It requires the lightest neutrino to be massless. It predicts that neutrinos are Majorana particles, which would be confirmed by the observation of neutrinoless double beta decay. It explains the cosmological dark matter as a right-handed neutrino, stable due to a Z2 symmetry, with a mass of 4.8 times 10 to the 8th giga-electron volts. And it predicts no primordial gravitational waves at observable frequencies, because it does not require inflation. The CPT symmetric universe is deterministic and time-symmetric. The future is as fixed as the past. Observers in each half experience time as flowing in one direction, but the global structure treats both directions symmetrically. This is an explicitly eternalist cosmology, a block universe in which time is not fundamental. The model is speculative, but it is mathematically coherent and empirically testable. Confirm the predicted neutrino properties or establish the absence of primordial gravitational waves, and the model gains support. If the predictions fail, the model is ruled out. What all of these ideas, superdeterminism, retrocausality, cellular automata, many worlds, time-symmetric cosmologies, have in common is that they dissolve the appearance of quantum randomness by appealing to a structure that is deterministic, or at least not fundamentally stochastic. The randomness is emergent, epistemic, or indexical. It arises from coarse graining, from ignorance, from your location in a branching structure, or your limited access to the underlying ontological states. None of these ideas has produced a testable prediction that distinguishes it from standard quantum mechanics. They are consistent with the data, but so is the standard view that quantum outcomes are fundamentally probabilistic, that the universe at its base is governed by chance. The honest edge is this: the experiments have not decided. The loophole-free Bell tests rule out local hidden variables, but they leave open superdeterminism and retrocausality. The cosmic Bell tests push any local realist conspiracy back to the early universe, but they cannot close the loophole at the Big Bang. The Leggett-Garg tests rule out macro-realism, but they do not tell you whether the underlying dynamics are deterministic or stochastic. The Frauchiger-Renner and local friendliness results constrain observer-independent reality, but they are compatible with many interpretations. The data underdetermine the ontology. What the data do establish is that if there is a deterministic structure beneath quantum mechanics, it must be non-local or retrocausal or superdeterministic. You cannot have local realism in the naive sense, with particles carrying definite properties and no faster-than-light influence. Bell's theorem closed that door in 1964, and the experiments since 2015 have welded it shut. But the doors to other forms of determinism remain open. They are narrow, and they require giving up intuitions about time, about causality, about free choice, but they are open. For some physicists, this is enough to justify continued work on deterministic programs. Gerard 't Hooft writes that his interpretation can and will be criticized and attacked, but he believes the project is worth pursuing. Sabine Hossenfelder and Tim Palmer write that superdeterministic approaches are still in their infancy, but they argue that dismissing them as conspiratorial is premature. Yakir Aharonov and Lev Weidman have spent decades refining the two-state vector formalism, showing that it makes predictions, weak values, post-selected quantum effects that have been experimentally confirmed, even if the ontological implications remain contested. For others, the lack of new predictions is fatal. If a deterministic interpretation reproduces all the same results as standard quantum mechanics and adds no testable content, then it is metaphysics, not physics. Parsimony favors the simpler theory, and the simpler theory is the one that does not posit hidden variables or retrocausal influences. The wave function is enough. Probability is fundamental. The future is open. Both positions are defensible. The question is whether you believe physics should describe only what is observable, or whether it should also explain why the observables are what they are. If you care only about predictions, then interpretations are a matter of taste. If you care about ontology, about what the world is, not just what we see, then interpretations matter, and the debate is substantive. The limits on computation and prediction are absolute. Chaos ensures that even a deterministic universe is unpredictable beyond a short horizon. Landauer's principle ensures that erasing information costs energy. Bremerman's limit, and the Margulis-Levitin bound cap the speed of any computation. The Bekenstein bound limits how much information can be stored in a region of space. These are not engineering challenges, they are constraints built into the fabric of spacetime and quantum mechanics. No advance in technology will overcome them. Laplace's demon cannot exist as a physical system because the universe does not have room for it. But the demon was never meant to be physical. It was a thought experiment, an idealization. The question it raises is whether the future is, in principle, determined by the present. Whether there is a fact of the matter about what will happen, even if no one can calculate it. The block universe says yes. Time is a dimension, and the future is as real.